Alright guys, so day one of actual content that we're going to be looking at, okay? Today is a huge day, it's a big day. Like I showed you on the calendar, we're going to look at limits, what they are. We're going to look at graphs of limits. We're going to look at tables of limits, otherwise the analytic form of limits, okay? So first and foremost, what I want you to do is I want you to understand that calculus will be shown 4 different ways. You're going to learn how to see and recognize calculus in these four ways, and you're also going to be able to replicate it in these 4 ways and teach back, okay? What do you think the G stands for? We're going to do it today. Graphs. So graphically, okay? So graphically, we're going to look at graphs and find limits from graphs. What did I say N stood for? Numeric. So numerically, and some of us don't know what numerically means, it's just looking at tables, okay? The XY tables that are vertical or the XY tables that are horizontal, which is kind of what you see right here with these XY graphs that are horizontal, or XY tables. What do y'all think A stands for? Algebraically. So algebraically, and last but not least, what do you think V stands for? This is the culmination. The word problems, verbally. Okay? So, looking at this, what I want you to do is I want you to follow very carefully and closely with me, because we're about to put this function into the calculator. Okay? So, let's go with this at the calculator over here. And let me access my calculator that I just signed in on. Alright, so here we go. Follow me closely, please. Oh yeah, just grab another one that works. Over here at the top right corner of this whiteboard, you will always, again, how many of you, be honest, how many of you came in and cleared your calculator? Nicely done, nicely done. Okay, every day I need you to, because otherwise you're going to get wrong answers on some of these things, okay? There was a student earlier today that was using a calculator, and for some reason someone changed it to degree mode. And it didn't work from something we did today, because calculus is in radian mode, okay? So real quick, when you do this home to menu C, okay, it will default it to radian mode. It'll clear the calculator and default to radian mode, and you're good to go. Every time, okay? Physics, how many of you take AP Physics or are taking it this year? That, Physics AP 1 or even Physics C, that's always in degrees, okay? But this class, AB and BC Calculus, will always be in radians, just FYI. Alright, follow me carefully. Home to menu, the letter C at the very bottom, and press OK twice. We are ready to rock and roll. Alright? So let's go ahead and put this calculator, or this function that we had over here on our notes, we're going to put it into this right here, this square root of x plus 4 minus 1 business. We're going to put it into our graphing calculator. Follow me carefully. Press 1 for new document. Press 1 to add a calculator page. Now, I'm going to press Control plus a page, otherwise doc, and I'm going to add a graphing page. So I'm going to press the number 2. So now it feels like an 84 now. You have a graphing page and you have a regular calculator page. Okay? Now, with me, we're going to put this function into the calculator. Follow me carefully. Control divide will get you a nice pretty fraction just the way you see it on your paper. And I want you to do Control x squared to access that square root. And you're going to do x plus 4, kick out to the right, minus 1 over x plus 3. Now, I will ask this, please. If you fall behind, try to not ask the person next to you. Just look over your shoulder, their shoulder, but try not to slow them down. Just put your calculator down, sit, and watch, and you can join in on the next problem, okay? If you fall behind. Because here's the thing. I really hope that you don't just frantically copy all these notes, because you will not have time to ask me great questions, okay? That's why I'm recording, because a lot of times I would prefer you to listen and observe and watch and do whatever you can. You can record and fill your notes later if you need to, okay? But if you can get it here, you're good to go. All right, so here we go. When I press enter, there's my graph, okay? So what I want you to do is I want you to soft mouse this keypad and go right on top of the graph, and you should see the hand open up. And if I press and hold that keypad, it will grab that function that I can now soft mouse and move out of the way. That's just my OCD. I just want to move it out of the way, okay? Now, from our notes, we're going to analyze those values, okay? So all of these values, as far as the x's are concerned, we're going to put them into the calculator, all of these, and we're going to see what y values do they spit out, okay? We've done this, hopefully we've done this on our 84s back when we were in Algebra 2, okay? So here we go. Let's go to the calculator and press Control-T to add a table. From here, I want to set my independent variable set to ask. Okay? So I'm going to press Menu, 2 for Table, 5 for Edit Table Settings, and scroll down to where it says Independent Variable, and I want to scroll over to where it says Ask, and then just press OK. Notice how it cleared all of my x inputs, because now it's waiting for me to give it values. And from our problem that we had, those values are going to be the negative 3.1, enter, negative 3.01, enter, negative 3.001, enter. And then let's do the other three. Remember, these are those values that we got from over here, okay? So we have negative 2.999, we have negative 2.99, and then we have negative 2.9. Okay? So guys, in your calculator, what we're going to do now is we're going to transfer over to our notes those values that we got. First off, notice how to read a limit problem, okay? So listen carefully. It's all about approaching negative 3. Let me tell you what this means. Let me highlight it a little bit better. If I had a number line right here, and this right here is negative 3, what number would you say is about right here? Just guess a number. Negative 5, right? Negative 5? How about right here? What would that be? Like a negative 2 or negative 2.5, right? So looking at this, what we're doing over here is that we're approaching negative 3 as close as we can get to negative 3 from the left side. Very important. Over here, we're approaching negative 3 as close and closer as we can from the right side. That ultimately, the answer to this question will occur right here, and it's basically what is the y value that you're going to see, like the pattern approach. Okay? So here we go. Let's go ahead and fill in these blanks from the tables values that we got from our calculator. Whenever I put in negative 3.1, I got a 0.513. Again, that goes back here, right there. Now, from here, what I'm going to tell you right now, you will either round or truncate all answers in calculus all year. Okay, let me show you what that means. Rounding means this. If I have a 4,99875, and I'm rounding to 3 decimal places, I would round this to 0.4, sorry, what would I round that to? 0.5. I would round that to 0.500 because this 8 right here made this 9 round up. if I truncate this, it means I'm not going to round. I'm just going to cut it off, and whatever the first three numbers were, that's what I'm going to write down. Okay? So the truncate would be 0.499. You're only allowed to be 1/1000th of a point off on all of your answers in calc. Okay? If you're 2/1000ths of a point off, it's wrong. Okay? Just know that that's the accuracy level that we're going to be achieving all year. Any questions so far? All right. I'm a rounding kind of person, so all my numbers that I'm going to do, I'm going to round them. Okay? So I have 0.513, 0.501, 0.500. And then I have 0.500, and I have 0.499, and finally the last one I have is 0.488. Okay? Can someone tell me by looking at this table what would be the answer that the y value is trying to approach? Yeah, you could just say it out loud. 0.5, right? Yeah. So 0.5 is going to be the answer there. Otherwise, 1/2. Go with me? So the answer to this entire limit is 1/2. Now, let's go ahead and graph this real quick. A quick sketch shows that it probably starts somewhere around here. It looks like this. It's an inverted square root function. And if I were to give it some scale size, I could say this is 1. And I could say that this is about, let's say, 1 is here. As I approach -3, it's going to approach 1/2. Go with me? So as I approach, and I'm going to blue color coordinate it so that you understand it, from the left on the graph, and as I approached from the right on the graph, that y value that it's wanting to become is right here. And what is that y value again? 1/2. Okay? All right. So let's practice just a little bit. We learned it by a graph. We learned it by a table. Now let's learn how to read this. Okay? I would say the limit as x approaches -3 of that. Okay? Or you could say the limit of that as x approaches -3. Why do I want you to understand how to read it? Because I will give you oral problems sometimes that you have to write what I say. So you have to hear it very carefully to be able to write out what I say, because I'm not going to give you sheets of paper, and we'll compete against teams at times, okay, for bonus points. What are they? They're bonus points on the test. 5 bonus points, 4 or 3 bonus points, stuff like that, okay? So you will compete in that respect. Every single test, 2 of these 3 groups will win, okay? And you'll win points, 5 or 4, okay? So, here we go. Let's go ahead and move on to question 2, unless there's a question of what we just did. Okay, so question number 2. Now listen, guys, I know this calculator very well, and I'm going to show you a lot of stuff with this calculator that makes things easier, not just to get to the answer, but to understand, okay? Follow me very carefully. I don't like the graph. I don't like it. I don't like the graph because the table that we were looking at, it takes kind of forever to set that independent variable to ask and so on and so forth. I don't like to use this table as much, okay? So follow me, please. I want you to, let's say, Control-T to get rid of that table. And now we're going to press Control-Left arrow so that we can jump over to the first page. Okay, so Control-Left arrow. Now we're back on the calculator page. Are you with me? All right, so now, again, I don't like that, so what I'm going to choose to do is I'm going to choose to put this function not into the graphing part, but I'm going to choose to store that function. Okay? How many of you have stored in the calculator ever? Okay. When you store in the calculator, chances are you only stored a number. Okay? Now you can store functions, which is awesome. Okay? So as far as functions go, you can label them f of x, you can label them g of x, whatever you want. Watch what I do. Okay, so let's go to the calculator. Let me take a quick picture so I know what I'm going to be inputting. So a quick picture of the problem. And now let's go to the calculator and start storing it. We're going to put in, follow me. Okay, so if you got lost, jump back on, okay? So control divide. And we're going to do the sine of 4x. So press that trig button. It's right here, guys. Look up here. That trig will access all of them. And we're going to do the sine of 4x. And it's going to be over x. Now, how do I store this function? I'm going to press the blue control button. I'm going to press bar or for variable. Otherwise, it's accessing those three blue letters is what I'm doing. And that's STO for store. Okay? And I'm going to store it as f of x. Please remember to put parentheses. I have probably said in this class, of means to multiply 9 out of 10 times. This is f of x. Remember, there's no multiplication there. I'm storing a function. Let's press enter, and it says it's done. It's now stored. Okay? Now, I don't have to go back and do that table the way I did before. I think this is much more efficient, and you will be far, far faster, in my opinion, than the ones that are using the actual tables. Now, we are going to approach 0. Okay? What values approach 0? What values? X or Y? X. So let's approach 0. And I want to get as close as I can. I want to be 1/10 away. I want to be 100th away. And I want to be 1,000th away. Okay? So guys, what would I put right here to be 1,000th away? 0.001. Think of it like a number line, please. There's x is equal to 0, and we want to be right close to it. Like right here, per se. We'll say 0.001. Okay? A little bit further away, per se, what will my next number be? 0.01. There's that 10th. Okay? And what's the last one, the furthest one away? 0.1. Now, on the left side, what would I put in this box here? Negative 0.001. Okay? And I know what you're saying, negative 0.999, that's just to the left of 1, not 0. So be careful with that. So this one's going to be a negative 0.0, and it's a common mistake, so no worries. So a negative 0.001. What's this next one going to be? Negative 0.01, and then negative 0.1. Now, I'm going to go to my calculator, and I'm now going to enter all of this into the calculator from left to right. Okay, so follow me closely, okay? Here we go. So in the calculator, I'm going to say, what's the y value, aka f of, a negative 0.1? Please press control before pressing enter. So you always get these clean decimal numbers, okay? And then I'm going to say, what is the f of a negative 0.01? Control enter. What is the f? Notice how I'm using this instead of the table of the negative 0.001, and you get that. Go with me, guys? So let's go ahead and go back to our table just real quick, and we're going to fill these values in. We have a 3.894. We have a, because we're rounding, 3.999. Then we have 3.999. Actually, this would round to what? 4. So this would round to the actual 4.0. Okay? So now let's keep going on our calculator. We're going to do the positive side now. Okay? So we'll say, what's the f of 0.001? What's the f of 0.01? What's the f of 0.1? And notice the progression of these numbers. So we will have 4.00, then we'll have 3.999, and then we'll have 3.894. It almost looks like a nice mirror image of it. Okay? Now, some of you may like the graph. And you can use the graph, you can use the table, you can use whatever you want. But please make sure you know how to do both. You have to know how to do both, not just, I'm going to pick my favorite, okay? Now, if I asked you to graph this right now, some of you are going to do this. You would go to the graphing calculator page by pressing Control to the right. You would press the Tab key, and some of you might actually put that equation in there. To me, understand how to use this calculator, because again, you will get fast with this calculator. Please go back up to f of x for the first one and delete that. And now, instead of typing this again, don't I have this stored already? What do I have this stored as? F of x. So get this. I could just put f of x right there, and it will read what it's stored as on page 1. They talk to each other. Okay? So our graph is going to look like this sinusoidal function that's oscillating. Alright? And it would look something like this. So it's going to oscillate back and forth, and then it goes like this, and then it goes like that. So the thing is that what value, let me put this in blue, what value is it going to approach as a y value? Anyone? 4. So that's the answer. The limit is 4. Okay? That is the said y value answer here, in between, and what it would be on the y-axis. Questions from what I've shown you? Because I've now shown you two different ways. I showed you analytically, or sorry, not analytically. I've shown you numerically, and I've shown you graphically. Okay? And now we're going to talk about it theoretically in just a bit. But are there any questions before I continue? Yeah.
How did you get the second tab on the top?
The second tab is going to be to open up a second tab. You're going to press Control, so this blue button, and then Dock to add a page. And let's say you could add another graphing calculator page, you'll press 2. I could press Control Dock, and if I wanted another calculator page, I could press 1. And the cool thing is they all talk to each other. When I save on one, it'll save on all of them. You with me? It's really cool stuff. And like whenever you do spreadsheets and regressions like you did back in Algebra 2, they all talk to each other as well. Okay? Alright, so let's go ahead and go to our next example. And I want, Braden, how do you read that?
What is the limit of x, or what is the limit of f of x as x approaches 2?
Perfect. He said, what is the limit of f of x as x approaches 2? That is correct. Okay? Nate, how else could I read that? What I have boxed right here. Kelly, how else could I read that? Close. So this one could be read as the limit as x approaches 2 of f of x. Okay? So let me read them both ways. The limit of f of x as x approaches 2. So that's like the limit of picture f of x and then approach 2 from both sides. Or you can say the limit as x approaches 2 from both sides on f of x, wherever f of x is at. Okay? Means the same thing, okay? Alright, so what I want you to do is I want you to see the domains of both of these. This is a piecewise function of two functions. Okay? First of all, notice the domain. If I were to graph the domain the way we did way back when in Algebra 2, we know this is when x is not equal to 2. So if 2 was here, it's basically everything else. That's what this is showing. You agree? Okay. What is the other one showing? When x is equal to 2. Okay, so this is just saying at one specific location. Okay, so here it's just going to be at x is equal to 2. Now, a lot of times, and someone asked me this question earlier during second period today, will we be able to use calculators on our limits test? What do y'all think the answer is? Actually, it's going to be no, because by then we're going to have a lot of algebraic manipulation of how to do these by hand through algebraic manipulation, okay? You will have sections later that have calculator, and that's what we're teaching you these skills still with limits, but it's a good way for us to introduce the idea of a limit by using the calculator with the tables and the graphs, okay? All right, so let's think about Algebra 2 transformations. What's the parent function of what I just boxed? Parabola, x squared, quadratic, right? Shifted what direction and how much? Up 1. So don't draw this yet. If I drew this, what is wrong with what I've drawn right now? There's a point at x is equal to 2, and there should not be a point at x is equal to 2, right? Okay, we should have a gap, a hole in the graph at x is equal to 2. So let's go ahead and create that just real quick. Now, can someone tell me what would the y value, if it existed, what would the y value have been if 2 existed on this graph? What would it be? Anyone, just say it out loud. 5. So to me, because look, if x equaled 2, 2 squared would get 4, plus the 1 would give you 5. No worries. So look at this. This is what I call a what if moment. You're going to use this a lot when we do continuity as well. It's like building linearity and continuous functions and whatnot, okay? So this what if moment tells me that this would be 5. And the reason why I want to teach it to you so early is because I want you to be able to do these graphs very, very clearly without needing a calculator, okay? Let's graph this other one. I'll box it in blue. What am I going to graph? The point. So, real quick, do y'all agree that this x squared plus 1 looked like a graph that was shifted up 1 unit? Okay. What does this 3 normally represent? It normally represents y is equal to 3. But we're not defining it on an infinite domain. We're only defining it at 1 point. You with me? So only 1 point will exist, and it will exist as the point 2, 3. With me? Alright. So from this, oops, it'll come back. So from this, what we're going to do is we're going to analyze by this graph what would the answer be to this question. Are we good? Alright, so real quick, what I want to do is I want to introduce and show you, remember the both sided that I was talking to you about? I even shaded it. If I approach from the left, look what you're going to do. I'm going to approach 2 from the left. Notice the notation. What do you think the most common mistake people read this as? Negative 2. That's not negative 2. That's approaching positive 2 from the left. Let me show you with highlight. Okay? Now if I approach positive 2 from the right on the same function, I'm now going to look at approaching from the right. I want you to approach this x is equal to 2, but I want you to jump on the functions. In other words, jump on the ride. Okay? Think of it as a roller coaster if you like. So if I jump on the ride and I'm approaching, look at this. This is all x is equal to 2 right here. And I'm jumping on the ride and I'm approaching from the left. Can someone tell me what does the y value want to be? 5. Okay, so you're going to put 5. And if I approach from the right by jumping on the ride, oops, again the same thing. Can someone tell me what does the y value want to be? It wants to be 5. Okay, so these right here are one-sided limits. From the left, from the right, and I call it making an ET moment. How many of you have ever seen ET? So ET phone home, right? So you're making that ET moment. If they touch, then the general limit has just been made. If they miss, the limit does not exist. You with me? If they touch or want to touch, the limit will exist. Okay? So we're going to say this right here, guys, is a general limit. Can someone tell me what sign do y'all see right there? Nothing. You don't see a positive saying it's coming from the right. You don't see a negative saying it's coming from the left. So if there's nothing there, what does it mean? It means both. It means both have been tested. And if they equal the same, guess what answer we're going to put right here? 5. Okay? Graphically, numerically, I think that's the fastest way that we can develop the understanding. Then we'll start going into a little bit more theory here in just a bit. But are there any questions right now from what you have? Okay, notice the keywords that I'm saying. What does it want to be and things like that. Whenever we get to that theory part, hopefully that helps. All right, let's look at this function. All right, Ryan, what do you think this function would look like if you could not use a calculator? An absolute value, so that someone said that in second period as well. And don't write this down yet. I just want to see what you're thinking and how you interpret it. Keep going. Someone take off with where she left off. What else could we possibly kind of think would happen with this graph without using the graphing calculator? It would probably shift 3 units to the what? To the left. Because what we know of transformations, right? And then if it shifted 3 units to the left, someone said in second period, it would have a removable discontinuity at what value? -3. So at -3, they said there would be a hole in the graph. Okay, so please don't write this quite yet because this is not the graph. Okay? So, can someone tell me what the answer to this is? Plus or minus 9. Don't say the next one because you were in last class, okay? So, the next one that I have is this. Can someone tell me what the answer to that one is? Plus or minus 81. Okay, so don't forget the plus and minus. So looking at this, my point that I'm trying to make is that there is a positive and a negative form of that x plus 3. Okay, I'm trying to help you develop algebraic representation and notation so that you know how to cancel and reduce and all that by forms of 1 later. All right, so you know that when you have absolute value, you have a positive form and a negative form. And let me show you what I'm talking about. Here's a positive x plus 3 over the original x plus 3. And here's a negative form of x plus 3 over the original x plus 3. And why? Because of what we know knowledge, whoops, from this right here. Okay? So, guys, what does this cancel to? 1. What does this cancel to? -1. Don't draw this yet. Okay, so what I have is, I have a function that is either going to be a positive one or a -1. Don't draw it yet. Does there exist a discontinuity from what you see here? Yes. Where does it exist? -3. Why does it exist at -3? Because you can't divide by 0. So at -3, we need a hole in the graph of some sort. Does it look like it's going to be a vertical asymptote? No, it looks like it's going to be like a jump discontinuity. You with me? Now, you have 2 choices here. The graph will either end up becoming something that looks like this, or it'll be something that looks like this. You with me? It'll either be the gray or the blue. How could we tell without a calculator which one it's going to be? Go ahead.
Plug in.
Plug in.
One, and then negative 1 for x.
Okay.
See what works
So you just have to plug in 1 point. You don't have to plug in multiple, but 1 is enough. Okay? What number could we plug in here? I mean, there's no correct answer. What number would you plug in just to see what you would get?
0.
You could plug in 0. So if you plugged in 0 at the top, 0 plus 3 is 3. The absolute value is still positive 3. What would I get as a final answer? 1. So when x is equal to 0, I have a positive answer. You with me? So with that positive answer, that means I'm going to be above the x-axis, so I know for sure it's not going to be the blue going to the left. You with me? So if it's the gray, it's not going to be this blue going to the right. So this is my graph. It's a step function that exists at 3. Because of plus and minus form cancellations of 1 and -1, and also that jump discontinuity that exists at -3. And yes, we did test the point as we just did with x is equal to 0. All right. So now, Jordy, can you read the way we practiced earlier? How would I read that? That stuff, right? So yeah, no worries. You can say that stuff, the function. So yes, the limit as x approaches -3 of that stuff. Okay? Guys, what's the answer? It does not exist. Now remember what we talked about. Both one-sided limits must be the same answer for this general limit to exist. If I'm looking at the graph, and guys, please look at the graph, and I approach it from there, what's the answer? 1. And I'm just going to put f of x here, okay? So just think that this whole function is f of x. And now, if I approached it from the left, what would the answer be? -1. Are these two the same? No, so the general limit does not exist. There's no ET moment. So we'll put does not exist. Questions? Okay. So let's talk about some theory, because it's going to help us go to the definition of the derivative that I'm going to finish with today at the end of class. Pretend that do you ever remember what superpower that I said I would want to have, or what I would want to be on the first day of school? Wolverine, right? So Wolverine heals, nothing that happens, I mean, he's still going to be fine. Let's say that I have a 3,000 degree Fahrenheit iron in my hand. Okay, 3,000 degrees, that's hot. Let's say that I'm standing right here in relation to Christian. Okay, what do you think you feel right now? How much temperature, how much heat do you think you feel if this is 3,000 degrees Fahrenheit? Guess. Just guess. 2,000. How much do you think you feel now?
2750.
2750. How much do you think you feel now?
Like 3000.
What did you say? Like 3,000. Will he ever experience 3,000? If I'm approaching him but never hit him? No. So I can infinitely get closer. Remember how I showed you with the arrows that we're approaching these? These are big topics. So follow me. I hope you see where I'm going with all this. I'm getting infinitely close. Infinitely close to him, but without touching him. He will never feel exactly 3,000, but it'll be close enough. Do you agree? Okay. So now, that's what a limit feels like. Oh, I hope it doesn't feel like that. But anyway, so let's put Christian right here. Okay? And we're going to put him on a cliff. And the cliff, let's say, is 5,000 feet high. Okay? And the function, let's say, is right here. And we are going to approach, let's say, C. It's just any x value, okay? And the function continues down here. Okay, so here we go. So f of x is the shaded function that you saw that's right here and it's right here. This is going to help you make graphs easy, okay? So, on f of x, let's say that we are finding the limit of f of x as x is approaching c from that. What would that equal? 0. What I just did is I described jumping on the function approaching c from the right, not to the right, but from the right. What is the y value that it wants to be right now? It wants to be y is equal to 0. You with me? Now let's put Christian way up here on this cliff, right? And he's walking with his eyes closed. Okay? So he's walking and he's determining based off what he's been doing. He's been at 5,000. I'm still at 5,000. I'm approaching C. I'm trying to get very, very close. And if I were to touch C, does he know what's about to happen? He doesn't know what's about to happen. But that's not what the limit is. The limit is, what does it want to be based off of the trend? Okay? So if I did approaching C from the left, what would be the answer? 5,000. How about the general limit? Just approaching C. It does not exist because those did not meet at the same y value. Does that make sense? Okay. So let's try one more. Actually, let's go to this. All right. Guys, there is a huge difference between this and this. Okay? Sophie, what is A, f of 0, what does that equal from the graph that you see here? -4. Perfect. Now let's skip down to C. Okay, think about it. Arjun, first, how would you read C? How do you read that?
As x approaches 0 of f of x.
The only thing that he forgot to say that's very important is what? The limit. What is the limit? I.e., what is the y value that it's trying to approach? What is the limit as x approaches 0 of f of x? Arjun, what would the answer be by looking at the picture, find 0, approach it from left and right, and what's the answer? Does not exist. Because if I approach 0 from the right, anyone, what would that be? On the graph, approach 0 from the right, what's the answer? -4. How about if I approach 0 from the left? It's about 0.8, right? You could do 0.8-ish. You won't have 0.8-ish on your test. You won't, okay? Maybe more. So the fact that those are not equal, that's why it does not exist. Okay? All right, so let's go Taylor. What is B? What is f of 1? You could say it does not exist, but what are you used to saying from Algebra 2? Undefined, right? So let's use undefined for this, because there's a huge difference between undefined and does not exist. Undefined you use for points, where it does not exist you use for limits. Do you understand? So does not exist is for limits, and undefined is just for domain, location, position functions. Okay? Points. All right. D. Braden, how would I read this?
What is the limit of f of x as x approaches 1?
Okay. So looking at the graph of f of x, let's approach 1, and what would the answer be?
-1.
-1. So you are approaching 1. Here's 1. Let's approach it from the right and from the left, but jump on the graph when you're doing it. So approaching from the right would be here. Approaching from the left would be here. And what y value is that wanting to be as they touch? -1. Okay? So that's how you get it. I just want to make sure everyone is 100% on this, okay? Questions? Okay, so now let's go to, I think we have a couple more. Approaching -3 and approaching 5. So let's approach -3. Anyone? What do you think the answer would be if I approached -3? Does not exist. Because approaching from the left is going up to what? Infinity. Approaching from the right is going what? Negative infinity. Will they ever have an ET moment? No. So it's going to be does not exist. Now, don't let this one, but this is jumping into theory here in just a bit. Stay with me. Let's approach 5. So let's look at the graph. Approach 5, jump on the graph and approach 5. What do you think the answer is? Infinity. In this class and on your AP exam, please put this because that's the correct answer. In college, they would actually not want you to put that. They would also want you to put does not exist. Because guess what? Infinity does not exist. Okay? Don't let that confuse you though. What we do in AP is we show how it doesn't exist. Because there's two forms of does not exist. There's this kind of does not exist where it will infinitely never touch. And then there's another one where they're still going the same way, and that's what we call it infinity. So on your test, on your quizzes, please, if they're going to that same arbitrary point, put infinity or negative. Okay? All right. Questions? Okay. So let's come back over here. And what I want to do is I want to look at your interpretation of understanding. Let's go with, all right. This is the culmination, guys. The last 25 minutes, they're going to be a little intense, okay? But I want you to jump and stay on there with me. And if you can get it, I promise you, a huge part of what calculus is can be described in these next 25 minutes. Okay, here we go. Graphically and numerically, we've looked at average rates of change, and it all boils down to this thing right here. Okay. You've seen this equation. y2 minus y1 over x2 minus x1. Can someone tell me what is it about this equation that makes it an average rate of change? Don't be scared to make a mistake. What is it about this equation that makes it an average rate of change?
It's like a straight line.
It's not a straight, not because it's a straight line, but thank you for that. I mean, because there's different interpretations. It's not because it's a straight line. What other things do you see up here that will say it's an average rate of change? Not division. These are big questions, guys. These are big questions that are helping.
Takes the rate of the y and x.
He says the y and the x closer. You're getting closer. Okay, let me do something real quick. Beep. I just sang a note for 4 seconds. Beep. I sang a note for 2 seconds. Beep. 1 second. And if I get infinitely close to 0 seconds, I hope you see with what I'm doing with this equation. Say again? So, okay, so you're way ahead of me right now. Let's come back. So you're right. It's never going to be 0, but what makes this an average is that right there. You with me? So let's say that you had 10 grades in the grade book. What are you dividing by? 10. 10, right? If I have 3 grades in the grade book, what am I dividing by? 3. So it could be 3 minus 0. It could be 5 minus 2. You with me now? It's between 2 points. So between 2 points, that change in x is this b minus a. Are y'all with me? For instance, here we go. Let's say that we have this graph right here. And let's say this is a. Can someone tell me what this would be? F of a. If this is b, what would this be? F of b. And now, this right here, this b minus a, is basically showing you, guys, that there exists an interval that you're counting between that makes it an average. You with me? If I looked at the slope, that's the average rate of change. But what if I told you I don't want the average? I'm a cop at Kroger that's clocking people as they go to school just to make sure they're driving the speed limit. And when I clock you, it gives me your speed. Is it giving me your average speed? No, it's giving me your speed at a what? At that specific instant in time. You with me? 1 instant. Can someone tell me how long an instant lasts? Oh, that's a big question. Let me ask that again. How long does an instant in time last? No, the instant that we're talking about. Not a duration, not an interval. A 1 instant in time. Think about it just for a little bit. I'm going to build to it, okay? Whenever you guys are taking Snapchats or taking selfies with Instagram, whatever, you're taking an instant in time. You really are. You're capturing an instant in time. Remember going back, like if I recorded a video, am I capturing an instant? No, I'm capturing something that has duration to it. But an instant is just 1 point. Do you agree? Okay, here we go. This is where the mind's going to go crazy a little bit. Stay with me. An instant is a point in time. Do you agree? Okay. We live in a 3-dimensional world. Length, width, height. For there to exist 3 dimensions, there must exist 2 dimensions. Do you agree? Okay. For there to exist 2 dimensions, there must exist 1 dimension. Do you agree? What does that look like? Straight line. So I had length, width, height. Whoops. Let me highlight that. I just had length and width. Now I just have length. For there to exist 1 dimension, there must exist 0 dimensions. Do you agree? He was in the 0th dimension. Anyway, so for there to exist 1 dimension, there must be 0 dimensions. What does a 0th dimension look like? 1 point. But as soon as I draw that, it has dimensions. Because 0 dimension means you don't have length, you don't have width, and you don't have height. So a point that you've been drawing since Algebra 1, guess what? Theoretically, you should not be able to draw it. Because a point is 0 dimensions. What else up here should you not be able to draw?
1 dimension.
1 dimension. Because a line has duration, but it does not have length or height. Right? That's cool stuff. With that being said, if these selfies that we take are instances in time, and our lives are infinite instances tied together from birth to death, And each of these instances don't exist. Do we exist?
It's a simulation.
Are we here? Just a question. So anyway, let's go back to this graph right here. And that's some cool stuff, though. Nice answer on that. What I'm going to do is I'm going to show you graphically what instant in time, an instantaneous rate of change is going to look like. Okay, so here we go. If this is A, f of A, and this is B, f of B, which is that slope right here, but I want to know what is the slope or the instantaneous rate of change at A. You with me? I'm trying to find out what's the slope at A. It would look like this. And let me tell you why. Okay? First of all, remember how close we got to these limits today? We got 1/10 away. Not good enough. We got 100th away. Still not good enough. We got 1,000th away. It was good enough, but I mean, how close could you get? You could get infinitely close, right? Now, so let's get closer. So this right here, this change, how far they're away from each other, x-wise, I want to bring it closer together. So let's not look at this point right here. I want to get on the graph and get closer to this point in green. My goal is to get as close to this green point as possible without touching it. If I chose this point, then the secant, otherwise the average rate of change, would look like that. Notice the steepness of this. If I get closer and picked a point here, it would look like this. Go with me? This slope that started as a gray slope here will become less steep, less steep, less steep, and will approach the blue slope. Do you agree? Now, will it ever actually hit the blue slope? No. Why not? Because it's an instant, and you would be dividing by what if you hit the blue? By 0. Can you divide by 0? No. But what did we learn today? That we can get infinitely close. A limit. So we're saying that the bottom will not hit 0, but we're going to try to get to 0 as close as possible, infinitely close, without actually hitting 0, because then we would be dividing by 0. So this h is basically that error that I just showed you that exists as far as 2 points approaching each other. You're trying to approach it as 0. Okay? So guys, if two slopes are so close to the same thing, so super close, and I'm talking about you could use the world's most powerful microscope and you could still get closer. You could still get closer to that tangent that it wants to be. We say that they're so close together that they're equal. Are you with me? So that will tell you our instantaneous rate of change. And that's like that radar gun as far as a cop taking your instantaneous rate of change. Questions? Yeah?
So the formula up on the board is instantaneous rate of change?
Yeah. This is instantaneous rate of change. It's called the derivative. It's called the derivative because the derivative is measuring at an instant what is your rate of change. Can someone tell me the application? How many of you are taking physics this year? Okay, here we go. What is the average rate of change between two positions called? Displacement. Ooh, I mean, you're good on that, but the average rate of change between two positions is called what? Velocity. Change in position, right? Over a period of time. Change in position over a period of time is going to be called velocity. Okay, so let's say like it's f of b minus f of a. This is an average velocity. Go with me? Now, the way we show this right here, okay, that she was asking, I can't see your nameplate, but that she was asking in the back, this is called a derivative. We call it f prime of x. And f prime of x is a velocity. You with me? So now what if I said, what is the change, so let me say this, the change in velocities over a period of time? The change between two velocities over a period of time. What do we call that? Acceleration. Okay, think of it, you're driving down the road, you have your cruise control on 60. There's your velocity of 60. And over the next 20 seconds, you're going to change your velocity to 80. Don't, but be careful. You're accelerating. You with me? So the change in velocities is going to become acceleration. And there's one more. What's the change in accelerations going to become? It's called the third derivative, called a jerk. Okay? And the jerk is that feeling that you feel when you hit turbulence. All of a sudden you're like, whoa, that kind of feeling. Or you're on an elevator and it's that dropping your stomach kind of feeling. That is the jerk. Okay? Questions? The application is this. Ultimately, we want to predict the future. And a lot of times calculus is used to predict mechanic engineering futures. To where, let's say, in 3 seconds, I would be able to know the position at that 3 seconds. I would be able to know at that same 3 seconds what is the velocity that that particle is moving at. And at that same 3 seconds, I would be able to calculate how fast is it accelerating at that specific instant. And all of this deals with what you learned today-ish. Questions? At all? All right, so let's answer some more questions from notes. So let's go to these right here. We're going to go through these kind of fast, so here we go. The limit of f of x as x approaches 2 on this graph. You don't see these on your notes, okay? So you'll have to look up here. So let's approach 2 on f of x. What is the answer, everyone? 1. Okay? Let's do the next one. Let's approach 3 on the graph. What is the answer? 2. Let's approach 5/2 on the graph. What's the answer? 1/2. Let's approach 1 on the graph. What's the answer? Does not exist. Don't be shy. Be very confident, okay? Good stuff. There's more. If I approach 0, what's the answer? 1. If I say, what is f of 2 on this graph? What's the answer? 1. If I say, what is the limit as x approaches 2? What is the answer? 2. Notice, this has an open dot. There's an open dot here at 2. But this is still 2. Why? It's where it wants to go to. That's the limit. What does it want to approach? It's the nearness versus the atness. So look at f of 2. It's at 1. The nearness, the limit, wants to be at what? 2. With me? Alright, so let's go now to more. If you understood today, these are easy. Otherwise, they can be a little bit challenging at times. Let's approach 2 now. What's the answer? 1. Let's approach 3. 2. Oh wait, are these the same?
Yes.
Oh my gosh. Alright, here we go. Jump discontinuity. Look at the graph. Remember what I was telling you from before of how you can build it? I wanted algebraic simplification for you to start looking at that, but that's the graph there. Is it a limit? Nope. It's a jump discontinuity. Doesn't make that ET moment. Over here. what would you write down as an answer on testing on your AP exam? Infinity. In college you would write does not exist, but here you will write infinity. Okay? How about here? This is a graph that does this. Infinitely does this. So if I were to approach 0, infinitely just get closer, it doesn't hit. It won't stop. Infinitely means it won't stop. So this is why the answer on this would be what? Does not exist. This does not exist is the same as like an infinite discontinuity that could look like this. You with me? The same thing. They're infinitely away from each other. That's what this does. Because it will never actually hit. Alright? Those more tables. There's a couple more graphs. I think, yeah, these are different. These are different. Alright, the first one. Let me see, Alec, read that for me. How would you read that?
The limit of f of x as x approaches 1 from the right.
Perfect. And what's the answer?
1.
Yes. Arjun, do the next one. Read it and then give us the answer, please. And what is the answer? Zero, right? Matthew, can you read the next one, please?
What is the limit of f of x as x approaches 4 from the left side?
And what do you get?
I think it approaches 1.
Yep. So as you approach, as the x approaches 4 from the left, the y approaches 1. Okay? Danny, can you read the last one for us, please?
The limit of f of x as x approaches 4 from the right.
What would that be?
1? No? Wait. Does not exist?
Okay. Does anyone have a different answer than does not exist? What would the other answer be if you did not say does not exist? Undefined. But undefined is not the answer because undefined deals with points. And what did she just read? A limit. So that's what we don't use undefined, we use does not exist. Okay? Perfect. I believe we have a couple more. Let's look at this one. Approaching 0 from the right, we get 9. Approaching 2 from the right, we get 2. Approaching 2 from the left, you see 3. At 2, it does not exist because of a jump discontinuity. Approaching -2 from the left is 4. Approaching -2 from the right is 1. Are we good to go, guys? Solid.